All right. Thank you very much for the nice introduction. And indeed, we are going to talk about medical robots, and we are going to talk about AI and behavioral autonomy. Yes, we are going to talk about all of that. But before we do that, let us give a bit of context and why are we actually doing this? So, did you know that coronary heart disease is the leading cause of death worldwide? It actually kills one person every 6 seconds. 1 in 5 men and 1 in 6 women actually die from this disease each year. And it is not actually for the aging population. It is also for the young population. 2 out of 10 deaths are actually on people younger than 65 years old. So what is coronary heart disease? This is your heart. And highlighted now are the coronary arteries. The coronary arteries, actually, their purpose is to bring oxygen to your heart. Because of life choices like smoking or an unhealthy diet, you can get some plaque on your arteries. This can limit the blood flow, and it can actually fully prevent the blood flow on your arteries. So, talking about computer vision, with an X-ray machine, the doctor is actually going to look at your heart, inject a special type of dye, substance, and he will actually notice that there is this blockage in the artery. So then he knows actually that you have formed this plaque in your artery. This is the diagnosis. So what happens next? Next comes the treatment. So then the doctor is actually going to put a catheter, a wire, and a catheter inside your arteries, inside your heart. He will inflate this balloon catheter, and then he will actually try to push out all the plaque at the sides of the artery, and then he will try to keep it in place with this stent that you see in the picture. So we at Philips actually create the systems that help with the diagnosis and also with the treatment of this type of disease. This is why we are here now. So let us have a look at actually how the procedure looks like. So now in the video you see from the robotics perspective that the robot is completely outside while the doctor is preparing the patient. So the doctor is really preparing the patient for the procedure, and the robot is totally outside his working space. Then he will do a puncture in your arm, he will put a needle, and then he will bring the robot in. So now the robot starts actually interacting with the physician. He will create a roadmap such that he can arrive from your arm to your heart and then perform actually the placement of the stent. So he will inspection it from different angles, he will try to see where the blockage is, and then he will place the stent. Towards the end of the procedure, then the system is actually going to rotate around your heart to check that there are no leakages, that there are no punctures, and actually that the stent is correctly put in place. What you see there is actually the robots that we create at Philips. Again, to help with the diagnosis and also with the treatment of the patient. And what you see there is actually a robot that collaborates with humans, that interacts with humans. It is not a robot that we have at the back and then we bring the patient to the table with the table and check what is wrong and where it is wrong. No, we have a robot that actually works with the physician at the same time. So this is why we are doing this research now. We want a full synergy between the physician and the doctor. Sorry, the physician and the robot. We want them to really cooperate together. And we want the robot to move safely in this environment. Now, for the purpose of the video, of course, you can see that the environment is quite clean and there are not that many people working around. Well, in reality, it's a little bit different. So you can imagine that the challenges of achieving these goals are quite difficult. So how are we tackling them?
we are tackling them by performing more and more research on the scenario that you just presented. And yeah, as Carlo mentioned, there are many research questions that the situation you just described proposes. And we need to focus our collaboration to get to tangible results. And we decided to start our research collaboration focusing on 2 pillars. The first pillar is autonomous navigation. Why? Because, first of all, autonomous navigation is the ability of the robot to move from place A to place B, while autonomously avoiding obstacles on the way. And the fact that a robot is able to decide by itself how to avoid obstacles enhances safety. Because in a scenario in which a robot shares the same space with humans, you never ever want that something bad happens to the people that are there. We can also go one step further and say, we don't just want to have a robot that moves by itself, but we want to have a robot that is able to actively participate in the surgical procedure at hand. And that is why we are investigating human-robot collaboration as well. Now, let's see how we are addressing autonomous navigation.
If we decompose what we just saw in the video into small steps, let us start with the setup. So in order to perform these procedures, the first thing that we need is, of course, a table, a monitor to see the X-ray images, and the robot, of course, that will help the physician. The next thing that we need, well, a patient, right? We are going to do the procedure on a patient. And then is all the medical team and equipment that will actually perform this procedure. It actually consists of 2 or 3 doctors, the nurses and the technicians, and the anesthesiologists with the anesthesia card. One step further, we are going to perform a radial access. So we are going to actually bring the robot from the parking position close to the arm, such that it can actually start performing the, I am being attacked, such that it is, that the procedure actually can start. So the robot has to navigate from the parking position to the arm. In some cases, the physician might be left-handed or right-handed, so he might prefer one side of the table or the other. Or because of the procedure, maybe you cannot enter from the arm, but you want to enter from the leg. In that case, you are going to perform a femoral access. So it's actually the robot going from the parking position to the leg of the patient. So just the starting position, if we just want to automate the starting position, you can see that it is actually quite a tricky task. It is going from the parking to a different position according to the preferences of the doctor. So how can we address this?
Hello?
Yes.
Yeah, thank you very much. Well, we address that by first understanding what makes the problem of autonomous navigation difficult. Well, first of all, creating an intelligent machine that is able to manipulate the real world is very difficult. And perhaps we don't realize this difficulty because we as humans don't see it. We know how to interact with the world. We know how to perceive the world. It comes very natural. But when we want to translate these capabilities into a machine, then the real problems start. Why? Because the environment in which a machine operates, this robot operates, is highly cluttered and highly dynamic. It means that you never know which type of obstacles, which type of scenarios the robot will encounter, and you need to be prepared to react to both of them. Also, a robot has physical limitations, so you cannot assume that it can achieve all velocities and accelerations you would like it to achieve, and also the type of movements that it can perform are limited. Our collaboration starts from results that were achieved by an impulse project that was run between Philips IGT and the Control Systems Technology Group, to which I belong. And one of the approaches that was proposed by the previous Impulse project to address the autonomous navigation problem is to set up a constraint optimization problem, which is called, in this case, it was an MPC problem, that was able to compute at every sample the ideal velocities and acceleration of the end effector of the robot, subject to some constraints. Well, we want to build and extend on the results that were achieved previously. How? First, we start considering the robot itself. In the previous study, it was approximated as a point mass that was able to freely move in space. But we know that when we address physical systems, then we also need to address their intrinsic limitations. And that is why we are extending these results by deepening the models that we have of the robot and by modeling the constraints that the robot is subject to. As we said a couple of times before, the environment in which this robot operates is safety critical and highly dynamic. And that is why we also want to further enhance the perception and environmental model capabilities of this robot. And as you mentioned before, computer vision, deep learning, is one of the techniques that is highly used, especially when perceptual input is constituted by images. But we want to go one step further, and as Marco mentioned, these type of systems are deployed in hospitals, in rooms that might have different layout, one and the other, and you don't know that upfront at design time. Also, the users that use this technology might have different preferences. Some of them prefer the robot to move in a certain way to have a radial axis, while others might have different preferences. Again, we can use a technique called learning from demonstration to gather data about how specific users would like this robot to move. We gather the data and then we try to approximate what would be the ideal path that this robot should move to. But if we only consider ideal path, then we have a problem. And the problem is, if an obstacle appears in front of the robot and the path is totally obstructed, then what should the robot do? Now, we also need to be aware and reactive to changes in the environment, as we've seen before. And one of the techniques that was recently proposed in literature to address both the way a robot reacts to a dynamic environment and the way a robot adheres to user preferences is to set up a reinforcement learning problem. In reinforcement learning, as Jim already introduced, a robot performs actions on the environment rewards or punishes this action based on the expected outcomes, and based on the feedback loop, the robot is able to learn an optimal policy. Now, to reward or to punish robots' action, we need to define a reward system. And in this case, demonstrations from users might help us might complement the definition of a reward system in order to enable the robot to learn. And that is what we are addressing in a project in which a PhD student is involved. Let's go one step further and understand the role of collaborative robotics.
So far, we have talked only about bringing the robot from the parking position to the starting position. We still have a full procedure to cover. So indeed, now the robot is already in, so we brought it from the park to the arm, but now it's time to continue with the procedure. How does it look? Well, now from the arm, the physician wants to move the system actually to the heart, where he is going to perform some images. We'll try to see if there are other blockages, for instance, or where the blockage is actually located, and he will try to position the system such that he can correctly place the stent. After that, then he is going to perform this 3D scan to check that he actually placed the stent properly, that there are no leakages, that there are no punctures, and that the work was done properly. To finalize, he is actually going to move the system from the patient all the way back to the park position. This procedure takes between 30 minutes and 3 hours, and when everything goes okay, usually the patient can go home actually in the same day. What a nice thing to do, right? You enter the hospital with a blockage in your heart, and exactly the same day you are going free of this blockage and you can continue with your life. And this was achieved with the help of that robot. A robot that is actually moving around the doctor, that is actually trying to obey what the doctor is actually telling him to do. For the next generation of systems, we don't want a robot that is only controlled and manipulated by the physician. We want a robot that can understand what's happening, what comes next. And that is for us the main goal with the collaborative robots. So, is it possible to do that?
Let's start researching. Okay, so what is a collaborative robot? What are the main ingredients that need to be present in order to define a robot a collaborative one? The first ingredient, context awareness. A basic form of context awareness is understanding where people are in the environment and where dynamic obstacles are. But this is not enough. This is just the first step. Because, people in the operating room, they have plans. They have wishes about what should happen next. In this sense, a basic form of context awareness is realized by understanding user intentions. And there are many, many different approaches we can use to understand user intentions. Machine learning, if we have good, trustworthy data, but also other methods, such as probabilistic reasoning. In probabilistic reasoning, one of the approaches is to define semantic location in the environment, and based on the observations, we compute what is the likeliest location a physician would like the robot to go to. Okay, now assume we have a good understanding of what people expect the robot to do. The next question is, what shall the robot do? And this is a typical decision-making problem. Typical questions that we can ask are, to which navigation goal should the robot go to? When should the robot start moving? When should the robot stop? Because something happened. Perhaps the goal location is obstructed. In general, the fundamental question is, how do we cope with a changing context? And there are many, many different frameworks that the AI provides to address the decision-making process. I expect you're all familiar with at least one of them, correct? Yes? Yeah, you perhaps 1,000. Okay. Now, we need to understand which framework or combination of frameworks is best suited to address the use case that we are targeting with our joint research. Okay, we have context. Context provides the background to take decisions. When these two elements are combined, we can realize something called proactive behavior. A robot doesn't wait for a user to exactly tell you what it should do and when, but it autonomously decides when to take action. If we combine proactive behavior with the execution of the physical behavior itself, then you have a collaborative robot. A robot that understands what's happening, takes decision about which actions to do, and actually performs them into the real world. This is a lot of work. And Marco and I, we are not the only ones who are addressing these questions. But we are building a community of students that share our enthusiasm and passion for medical robots. And we are coupling the students with domain experts from Philips. And we work together towards the achievement of shared goals. And these shared goals, they belong either to one of the two pillars that we have introduced before. At the moment, we have 2 running projects to enhance the models of robots that we have. one project on extensions of on the MPC techniques that we have just seen, and a PhD student that is dedicated on the learning from demonstration approach, as we have explained in the slide. And in these weeks, we would like to finalize a mini impulse project in which we are going to address collaborative aspects.
All right, so I just met Carmen during breakfast, and she was sharing with me the nice experiences of introducing Integris and the Allura and the PolyG systems. It was first introduced in 1989, and then we continued with the evolution of those systems up until 2017, which is the latest FlexArm system. So yeah, we started, it has been a long journey, but we are not shy away of innovation. And actually what we want to do is to go beyond the POC. So we really want to bring the innovation close to the products. We have seen it in the evolution of the systems that you see on the screen, but we want to bring it one step further, one step really into the future, in which the usability of the systems is actually based on collaborative robots, and the safety of these systems is actually based on the autonomous behavior that it can display. Because we believe
that we are enabling the future generation of medical robots with our joint research.
Thank you very much.
Thank you very much.
All right, thanks, Marco and Elena. I saw many questions coming in the chat, so hope you are prepared. The moderator. Yes, can you please check the questions? And can we please put the mic on?
Proberen.
Yes. Oh, there is a green light, but no sounds. So
It's not me, it's Charlie. It's the loose mic.
yeah, the handheld.
Yep. Yep.
Yes,
Okay.
thank you.
Thank you very much. It's a question from Sven van der Meer. Do you use real patient data to train the model? And if so, how do you get enough and not biased data so that the models are applicable on patients worldwide?
Which models are we talking about? Because we use a lot of models in this research. Yeah, so okay, we need models to control the robot and to understand its limitations. And for that, at the moment, we are building them based on prior knowledge that we have. In particular, we are investigating which inverse kinematic framework is best suited, whether position-based or velocity-based. But we really do this by modeling. And in order to enhance the robot models that we have, we might use data, but we are investigating this aspect with one of the master thesis approach on digital twin that we have just seen. With respect to learning from demonstration, what we need are not patient data. What we need are demonstrations from the user of the system, which would be the physicians themselves. Yeah, I hope this answers the question.
Thank you. The next question from Nicolas Michael. Wouldn't it be uncomfortable allowing the robot to make mistakes on a patient during surgery for the rewarding function to work?
First of all, I know Nicolas, so he's one of my students. Yeah, so so you never ever you cannot allow a robot to make mistakes. And that is why you need to allow autonomy as long as you can prove that autonomy is safe. If you cannot do that, then you need to rely to human supervision, which is also one of the points you were making. And I didn't talk about level of automations. You mentioned augmenting users, but we can also talk about desired level of automations. But that is something that we will take along in our research. So we need to understand up to which level we can make AI and the smart algorithm that we are making safe by leveraging different techniques. And when we cannot do that, we need to rely on human supervision.
Yeah. Okay, then a question which relates to this. What techniques will you use to qualify these autonomous robots in the medical domain and prove that they are safe?
That is a very, very interesting question. And we are debating actually on which type of approach should we adopt for safety. I cannot give you an answer right now because we are setting up dedicated research projects on that. I think a fundamental question is which type of safety assurance do you need at algorithm level, and which type of safety problems do you address at supervision level? And by supervision, it can be human supervision, but also supervisory control techniques that are well developed and well researched.
And indeed, the safety is critical. So you say up to which level do you want to accept some mistakes on the robot? Well, the level is 0, because we are talking about patients and we are talking about doctors. So there has to be a level in which we are comfortable with a self-operation of the robot while it is supervised by the human and while it is still safe to operate, yes.
Okay, thank you. Next question from Sven van Egmond. What would you define as the biggest challenge from a data perspective?
From a data perspective, it is not sufficient to collect all the data on the usage of the system, but you have to have the right data, right? As we heard from the previous presentation. It is not to create a data-driven model and then you have the answer to everything. You have to have the data from the usage of the system, from the degradation of the system. You have to have data from the patient himself. So it is about selecting the proper data, categorize it, and then create the right models from it.
Okay. Then another question, how do you define students' assignments and how do you safeguard the deployability of the outcome of students' assignments?
Should I take that one?
Please.
All right. So first of all, if you are curious, please talk to Elena, because we are always in search for nice students that want to join us and work with us. And then what we do is that we always create these pairs between the industry experts, the technology experts, and also with the students, such that we can actually create these pairs that bring both worlds together. And how do we deploy these techniques? Well, this is actually what we are aiming to do. We are not aiming to do some research that in 10 years or something like that we will see the results, but we are trying to create baby steps that we can always apply it to our products.
One final question, or?
No.
Enough for now.
Yeah.
Okay, thanks a lot.
Thank you so much.
Thanks, and yeah, we will talk to you in the coffee break, I think. So
Perfect.
Very nice. Thanks for for sharing the
Thank
content. All right.
Yeah, thank you very much.
So good to know is please keep asking your questions, and we will forward the questions that we cannot deal with now on stage to the speakers, so that they will be addressed anyway. Now we had to short coffee break. We will be back at 11:45, so 11:45. We will probably use that time to catch the aggressive fly on stage. We were also discussing whether maybe it is a mini drone of maybe one of the people at home trying to be in the area anyway. So well, we hope to give an update on that when we get back at 11:45.